Why are soap bubbles colourful? This might seem like kind of a random question, but the answer is actually so cool. First, there are two answers because light behaves in two different ways, either as an electromagnetic wave or particles of light called photons. This is called the wave-particle duality of light. So we're going to jump right in with the first answer. What gives soap bubbles their colours, assuming that light is a wave? If you've ever looked into a lake, you've probably noticed that you can see fish swimming beneath the surface, but if you shift your focus, you can see your reflection. That's because light partially reflects off a watery surface. The wall of a soap bubble is just a thin film of water sandwiched between two layers of soap. So when light hits the first surface, some light is reflected and some light goes through, just like the surface of a lake. Sometimes the ray of light that goes through will get reflected off the second surface. Waves have this property where they can interfere with each other. If they're both in phase, that is, if their peaks and troughs line up, they amplify each other in a process called constructive interference. If they're out of phase, that is, one of the wave's peaks line up with the troughs of the other wave, they'll cancel out in a process called destructive interference. White light is made up of all the colours of the rainbow, and different colours correspond to different wavelengths. Which wavelengths amplify and cancel out depends on the thickness of the water layer. This thickness varies all over the soap bubble, so different wavelengths of light are being cancelled out and amplified at different parts of the bubble, and that's why we see different colours in different areas. This phenomena is called iridescence, and it explains why some substances seem to change colour when sunlight hits them. But this is only half the story. It's a pretty satisfying explanation until you consider that light also behaves as a particle. Then everything we've said so far breaks down. To take an analogy, compare two billiard balls colliding to two water waves colliding. The water waves will often combine to make a bigger wave, while the billiard balls will bounce off each other and go their separate ways. Particles behave in a similar way. They don't interfere with each other, so they can't cancel out or amplify. To complete the story, we need to talk about something else that's partially reflective. Glass. You know when you walk past a store window and pretend to look inside, but are totally just checking yourself out? You can do that because glass, like water, is partially reflective. Scientists got curious as to exactly how partially reflective glass is. In other words, exactly how much light is reflected and how much light goes through, or is transmitted. To find the answer, they performed a simple experiment. They shone light through a block of glass and placed one light detector inside the block, which we'll call detector A, and one back near the light source, which we'll call detector B. These detectors were so sensitive that they could count the exact number of light particles or photons that hit them. Detector A counted exactly how many photons were transmitted through the glass surface, and Detector B counted how many photons were reflected. They found that out of every 100 photons they fired, 96 were transmitted and 4 were reflected. So glass is 4% reflective. The next question they asked was, naturally, how many photons would be reflected off two glass surfaces? Kind of like our soap bubbles, except with glass instead of water. This is where things get weird. What you might be expecting is that out of every 100 photons, the first surface would reflect 4 photons, as it did previously, and the second surface would reflect another 4 photons, making a total of 8 reflected photons. Which is what happened. Sometimes. But other times, for example, when the sheet of glass was very, very thin, no photons were reflected at all. This is already weird because when there was only one surface, 4 photons were reflected, and that surface is still there. So what happened to those 4 photons? Did they somehow know about the other surface? But it gets weirder. As the glass got thicker and thicker, the number of reflected photons changed, from nothing at all to a maximum of 16. You might be thinking, okay, that's a bit strange, but there's a pretty clear relationship. The thicker the glass, the more photons are reflected. But no, as they increased the thickness of the glass again, the number of reflected photons went back down, eventually getting back to 0. They increased it some more and it went back up, getting to a maximum of 16 again. This cycle repeated for more than 100 million tries, with glass over 50 meters thick. What? So remember how we initially thought that 8 photons would be reflected from the two surfaces, 4 from each surface? Well, overall it averages out to 8 because it cycles between 0 and 16, but it's only exactly 8 twice every cycle. So what's going on here? How can one surface reflect 4 photons, but adding another surface can either change that to none or 4 times as many? How does the photon know? The answer to all of these questions is no one knows. Physicists don't know why or how any of this happens, but they do know it's what gives soap bubbles their colours. Even when light behaves as a particle, the varying thickness of the bubble wall affects how many photons are reflected, just like the sheet of glass. This is a soap bubble illuminated with pure red light. See those dark bands? That's the exact thickness where the reflection cancels out. The really vibrant areas are where reflection is around the 16% mark. To see how different colours interact, here's an image of a bubble illuminated with red and blue light. Notice the different thicknesses reflect some colours more strongly than others. Here, more red photons are reflected, and here, more blue photons are reflected, while a pretty even amount of red and blue is reflected here, making a nice shade of violet. When sunlight, which contains red, blue, yellow and green light, shines on a soap bubble, the areas that strongly reflect each of these colours overlap and produce all kinds of combinations, which we see as different colours. The colourful effect of iridescence can be